In an earlier video, we explained that this simple circuit with an N-channel MOSFET down here and a pull-up resistor here functions as an inverter. However, having a resistor here is not a good idea. Basically, we want R to be large under some circumstances, and we want R to be small under other circumstances, and thus no value of R is going to be a good choice. Specifically, if the input to this FET is a logic 1, then that means that the FET is going to conduct, so it's going to pull the output down to ground. This means that we've got our supply rail going through this resistor going to ground. We are needlessly wasting energy through this resistor here. The smaller the resistor, the more energy we lose. So when the input is a logic 1, we want the value of R to be very high. The higher it is, the less energy we waste dissipating current through this resistor. The output's going to be 0, or the current through this resistor is just being wasted. On the other hand, if the input is a logic 0, then the channel is off, and so the output is going to be pulled high through this resistor. But if we were to connect this inverter to another logic gate, we saw in our last video that a logic gate, its input looks like a capacitor, and the larger the value of this resistor, then the longer it's going to take to charge up the capacitor, and the slower our circuit will react. In simple terms, a large resistor here limits the amount of current we can supply to the output, which limits the rate of change of subsequent logic gates. So when the input is a logic 0, we want R to be small. When the input is a logic 1, we want R to be large. So how do we choose R? Where we're heading is we want to have a variable resistance here that varies depending on what the input is here. If the input here is a logic 1, then this means that this FET is conducting, and so we don't want a small R here to waste energy. We want a very large R. If on the other hand the input's a 0, this FET's off, we want this R to be very small in value to allow lots of current to be able to be output here. So we want R to change. In fact, ideally, we want R to be replaced with a voltage-controlled switch. An ideal FET would look like this. We have got one voltage-controlled switch here, and we have another voltage-controlled switch here. This is the output, and depending on the input, we want that if the input is a logic 0, then we want this switch down here to be open, and we want this switch up here to be closed. If on the other hand the input is a logic 1, then we want this switch to be closed and this switch to be open. It should also be obvious that we never want both switches to be open at the same time, because that would leave the output just dangling, and we don't want both switches to be closed at the same time, because that would give us a short circuit. So what we require is that we need two switches and that they function dual to each other. When one's shut, the other's open. We can actually achieve this quite easily by using an N-channel FET at the bottom and a P-channel FET up on top here. Specifically, if we make some room here, we want to replace this pull-up resistor by a voltage-controlled resistor, and we know that FETs are voltage-controlled resistors, so I want to put a FET in here, and we'll explain presently why we want it to be a P-channel FET, and it's going to depend on the input voltage here. And don't worry about the sizes of the FETs being horribly different. They're supposedly identical FETs, just P-channel at the top, N-channel at the bottom, and we have ourselves an actual inverter. The input A, the output B. How does it work? If the input A is connected to ground, then this FET is off, so to speak. No current flows through it. If A is at ground, then we have our supply rail falling over. So for a p-channel FET, we've got source. A p-channel FET, its major carrier are holes. So in other words, the positive supply rail. So we're sourcing holes from the positive supply rail. That's the drain, that's the gate. Once again, it's the voltage between source to gate that determines how open or shut the channel is for a p-channel FET. So if A is at ground, we have a large voltage drop from source to gate that will allow the channel to conduct heavily, and therefore the output B is going to be our supply rail. So 0 in, 5 volts coming out, for example. Conversely, if the input A is at 5 volts, and this is 5 volts, then we've got a 0 voltage drop across our p-channel FET, so it does not conduct. It's an open switch. And if we've got 5 volts here and 0 here, we've got 5 volts across this n-channel FET from gate to source. It will conduct strongly, and that connects B to ground. So in this case, this switch is closed and that switch is open. So using two FETs, n-channel on bottom, p-channel on top, allows us to form, ideally, this circuit here with two voltage-controlled switches, and whenever the top switch is open, the bottom switch is closed, and whenever the top switch is closed, the bottom switch is open. This is true for our NAND and NOR gates as well. We saw in the last lecture how by putting FETs in parallel or series we can implement NAND and NOR gates. We replace the pull-up resistor up here with some p-channel FETs, and we arrange them in such a way that whenever the combined bottom switch is closed, the combined top switch is open, and vice versa. And that's precisely how logic gates are made using FETs. If this is the bottom half of a logic gate with two n-channel FETs here, then the top half has to be a voltage-controlled switch such that whenever this combined switch is closed, then this combined switch is open, and vice versa. So thinking about this for a little while suggests that what we need to do is try to use two p-channel FETs because they're on top, and we want to arrange them not in series but in parallel. So let's have a look whether this works or not. This is the design we're proposing, and A here are the same thing. I could have drawn a line here, but to keep it looking tidier, I just labelled them both A, and the same with B. These two wires are the same input. Let's see if this circuit works, and if it does work, what logic gate does it implement? We go through the four possible combinations for A and B, 0, 0, 0, 1, 1, 0, 1, 1, where, of course, a logic 1 means that the input is going to be 5 volts, and a logic 0 means the input's going to be 0 volts. If A and B are both 0, then downstairs we have that both our FETs are off, and so this combined switch is open. If A is at 0 volts, that means we've got 5 volts across this FET, which means it's closed, and the same for B. But regardless, even just one of these FETs being closed implies that this switch is closed. So in the case of A and B both being 0, the top switch is closed, the bottom switch is open. We don't have a short circuit, we don't have an open circuit, so it's functioning correctly, and we know that the output C is going to be a logic 1. It's pulled up to 5 volts. Move on to the 0-1 case. In the 0-1 case, we have at the bottom that the switch is still open. At the top, because A is a 0, then this first FET here is going to be closed, so the combined switch is closed. So we've got top closed, bottom open. Because they're opposites of each other, it's valid, and we see again that the output is a 1. The case 1-0 by symmetry is going to be the same. It works, and we get a 1 here, and that just leaves the 1-1 case. If A and B are both 1, then downstairs it means that both these FETs are on, so this is closed, and up here, because A's 5 volts, B's 5 volts, then we've got a 0 voltage drop from source to gate in both cases. So both these FETs are open. The combined switch up here is open. So again, it's a valid arrangement. The top's open, the bottom's closed, and we get C being pulled down to ground. So we get a 0 here. So we see that we have a NAND gate. I won't go through it, but if you were to put N-channel FETs down here in parallel, so the purple ones come down and change to N-channel, and if we put P-channel FETs in series up here, so the N-channel FETs move up here and become P-channel FETs, then we're going to get a NOR gate for essentially the same reason. In summary, we replace the pull-up resistor with a voltage-controlled resistor so that the pull-up resistor can be large when we need it to be large, and it can be small when we need it to be small. At least one person is going to ask, well, this sounds good, but what happens when we change our inputs from all 0 to all 1? So in other words, what happens when the top switch goes from being open to closed and the bottom switch goes from being closed to open? Won't we have a period of time when we have a short circuit? Well, remember that these switches here correspond to the ideal case. In actual fact, as A changes from 0 volts to 5 volts, we're going to get a variable resistor here, and its value might range from, say, in our SPICE simulations that we did, the value here ranged from about 1k to, well, we didn't actually show it, but let's say 1 mega ohm or something. And so as the voltage changes here at the transition point, for example, if this were somehow totally symmetrical, if we have 5 volt supply rail here and we had 2.5 volts everywhere, then the resistance here is probably going to be something like 10k, 100k. It depends on many factors, but the point is, say even if we had 10k here and 10k here, we have a 20k resistor between here and here. So yes, some energy is being wasted, but it's not a short circuit as such. How to minimize energy is an active area of research, and people keep trying to make improvements to how you build FETs. You have control over the length and the width, and how do you best build your FETs so that you minimize the amount of energy being used while preserving robustness to noise. But that's an advanced topic we're not getting into here.